Hi, today I will be doing this question, 42 trapping rainwater. So the question gives you an array of integers, and each element in the array tells you the height of the whatever you can call it, maybe the ground or the obstacles or whatever you want here. So for instance, for for this given input, the first element 0 tells that in the first position there's nothing, so height is 0. And the second place is 1, so second place 1. Third place nothing, fourth place 2, and fifth place 1, and then nothing, 1, then 3, and then 2, then 1, then 2, then 1, right? And it asks you, so when it's raining, and how much water, how much units of water can this obstacle or just can this thing trap. So here let's count it. So 1 1 plus 1 and plus 2 plus 1 and plus 1, so the answer is gonna be 6 for this given input. Okay, so from our first insight, we can definitely just do it in the most silly way, that we want to know, like, for each position. So let's just first write it down. So maybe like, so for each position, position 1, position 2, position 3, position 4, and position 5 and 6 and 7 and 8. So we want to calculate the water trapped by each position, and then we add it up, which will give us the final answer. So how can we do this? So actually, for each position, the amount of water it can trap is determined by the highest one on its right side and the highest one on its left side. We want to find like the smaller one between these two highest values, and we want to compare the smaller one of these two highest values with the value at this position. So for instance, for the first location 1, the highest one on its right is this one, so it's 1 1 2 3 4 5 6, so it's 6. And the highest one on its right hand side is basically nothing, so we can just say it's 0. And the smaller one between 0 and 6 is 0. Since 1 is larger than 0, then we cannot hold any water at this position. And let's see, for instance, for position 5, the highest one on its left side is at the fourth position, so it's 1 2 3 4, so it's 4. And the highest one on its right hand side is 1 2 3 4 5 6, and the smaller one between 4 and 6 is clearly 4. So the smaller one of the two highest values is 4, and since 4 is larger than 1, which is its own value, then we can hold water here. And like 4 minus 1 is 3, so we can trap 3 units of water at this position. And if we continue doing so, like for each position, we can finally add them up to get the final answer. However, this algorithm is not quite efficient. It takes n squared time complexity, since we need to literally go through all the positions. And for each position, we need to go through all the positions on its right hand side and all the positions on its right hand side. So it's basically an n-sized loop nested by another n-sized loop, so it's n squared. And so actually for this question, our aim is to actually finish our calculation within time n. Just we want to improve the algorithm to make it an O(n) algorithm instead of an O(n) squared algorithm. So basically there are 2 ways to do so. So the first way is to use 2 additional arrays to make the comparison more efficient. So here we can actually start 2 arrays. So let's see. So let's see, from here we start array 1, and from here from here we start array 2. Okay, so the rule here is very simple. So for each position, we just put the largest value so far recorded in this array. So for instance, here, for the first position, for the first array, just from the right hand side to the right hand side, the largest value is 1. Let me change the color so to make it more clear. So the largest value is 1. And then for the second position, the largest value note here is 1, 2, 3, so it's 3. And for the third position, although its own value here is 1, we still put the largest value so far here, so 3. And for here, 1, 2, 3, 4, so 4, 4, 4, and here is 1, 2, 3, 4, 5, 6, 6, and 6. And now the same thing applies to the second array, but the only difference is that this time we start from the right hand side. So here is 2, 6, 6, 6, 6, 6, 6, 6. And now what are we going to do with these two additional arrays? So now if we want to know how much water can be trapped by each position, for instance, for the first position, we just find the smaller value of the two numbers here, just in the array in the same position. So from the first array, the value here at the first position, we can call it just 0, since index starts from 0, or we can just call it the first position. So the value is 1, and from the second array, the value is 6. So here we clearly select 1, since 1 is smaller. And then we compare this value with the own value of this position, which is also 1. Actually, we just subtract the smaller value from the two additional arrays by the value of this position. So 1 minus 1 is 0, which means this position cannot trap any water, 0 units of water, which is true. And then for this second position is also true, so 3 minus 3 is also 0. And for this for this third position, so the smaller one between 3 and 6 is 3, and the value of this position is 1. So 3 minus 1 is 2. Oh, sorry that this drawing is not correct, since here clearly we can just trap 2 units of water. Right. So 2 is the right answer, like for this position. We can trap 2 units of water. And if you're still suspicious about this approach, you can just pause the video and try to calculate the rest of the positions, and you will find like this approach is absolutely correct. And but why? So actually, for doing so, the array from the left to the right and the array to the from the right to the left, we're actually just recording the largest position from the left and from the right of a given position. Things like for any position, like it's guaranteed that the value from the first array is just the highest value ever reached by all the positions on its right hand side, including itself. And the value from the second array, just like the blue array, guarantees that there exists a highest point of this value among all the positions on its right hand side, including itself. And I think the benefit here is that we don't need to really worry that what if the highest position is lower than the value of this position. since we definitely want to avoid like a negative value after subtraction, but here's no need to worry at all, since even if this position is the highest one so far, its its value is guaranteed to be included in the two arrays. So 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 the same number subtracted by itself gives us 0, so which means this position cannot hold any water, and it's actually true since the highest position cannot trap any water, and that's just quite obvious. So let's do the coding for this method. So first we need to create two arrays, so maybe we just call it left and right. Left equals to new int height.length, and the same thing, so call right. So we need first to write a loop to traverse all the elements in the array to fill the numbers into the two arrays. So like left I equals to max left. So actually we can, to avoid the trouble, we are actually comparing its current value to its previous value. So actually we want like to do this, right? Since if the previous value is larger, so for instance at this position, we just keep the previous value, which is 3. However, if the current value is larger, like in the first position, we add the current value 4 into the array. However, if we do so, we'll get an index out of boundary arrow, since the I starts from 0, and 0 minus 1 is negative, which is illegal. So actually here we can just start the I from 1 actually, and for the first position we can just manually put it in, since at the first time the array is going to be all zeros, and at the first position we definitely just put the value of it into the array, right? So left 0 equals to height 0, and right, so this is the last element, so 1 equals to height dot length minus 1, right? So far we are in a good shape, and also the same logic for the right array. The only difference is that this time we are going like we are going smaller and smaller. Right, okay, and then we finally need another loop to go through all the elements and like to calculate the result. I plus plus, and then here we need to initialize a variable to kind of to store the final result. So so we just go through all the elements. So result just plus, so the one from the so the minimum, so the smaller one from the two values retrieved from the two arrays, and then it needs to be subtracted by the height of this position, and I think this will give us the right result. Let's see. Well, here's an issue here, and so actually I'm just too lazy, kind of. I'm just copying everything, and here it should not just start from 1. Instead, it's just start from the second last element in the array. Oh, sorry, it's gonna be height dot length. Height dot length. Right. Height dot length. Right, okay, here we solve this problem in 1 millisecond. And so the time complexity for this algorithm is actually, so let's see, here we get an n, and here we get an n again, and here we get an n. So it's actually 3n, and actually we don't care about the constant. So the time complexity of this algorithm is on. Okay. However, here's a second way to do so, and to solve this problem. And the second way should be faster, should be even faster, slightly faster than the first way. So let's think about the question from another perspective. So let's just delete these nodes here. So let's consider this problem from this perspective. So actually we can just imagine, just this one is, I think it's a little bit more abstract. So we can imagine like there are two people standing from one at the start and one at the end. So for instance, here is the first people, the red guy, and here's the blue guy from the start and the end. And each time we only focus on the each time we only focus on the smaller one between the two elements pointed by two people, or we can just call it two pointers. So initially the elements pointed by the two pointers is elements number 1 and number 8. We first want to find the smaller one of the two, and if they equal, we just choose just right or left, just any of them. You can decide, just choose right or left. So we first want to find the smaller one between the two elements, and then we do the following operation on the one chosen. So actually we need two other variables to hold the max. So we need other two variables to hold the max of the elements of the height, the max height so far we have reached from the left side and the right side. So red max and blue max. Okay, so for the smaller one, we do this. Note that the initial value of the maxes are just zeros. So if the value of if the smaller value is larger than the max, then it's max, then we update the max. So for instance, now initially 1 is larger than the default value of max, which is 0. So we have to update the max. And then we move after the operation. So we move to the next position. Just these two pointers are kind of squeezing. They're moving towards each other. And then this time, the red one is 3, the blue one is 2, so the blue one is smaller, and now clearly we need to update our max. Right, then we move. So here's the blue one. And now 3 and 6, so we update again. So here it becomes 3. And then we move to here. And now things gets interesting. So now here 1 is smaller than 6. So again, we want to do operation on the right. On the red one, on the left hand side. However, this time its value is not larger than the max. So this time we just can calculate the water trapped here by subtracting its value from the max so far recorded. So 3 minus 1 is 2. And this is, you can see this is true actually. This is right. There are 2 units of water here. So why? Why this approach is right? So let's see that. Since now we are doing the operation on this element, which means that this element its own value is smaller than the right hand side. It's smaller than right hand side, and also so here actually the height of this element is kind of it's actually decided by the largest value on its left hand side. So here, since actually it's smaller than its the largest one is left hand side, so if it can hold water, we definitely want to look at like the left hand side, since left hand side is already larger than it, and we are also sure that its right hand side there exists at least one height that is larger than its current height. Actually, that height is even higher than the highest one on its left hand side. Since if let's think about it from the opposite direction. So let's see that what if actually now, like in the third position, we know like the highest one on its left hand side is 3. So what if all the elements, all the height on its right hand side are smaller than 3? This cannot really happen, since otherwise we won't be operating on this one, and we won't even be operating on the second position, on the highest one on its left hand side, if there's nothing higher than it on the right hand side, right? Since we always operate on the smaller one among the left one pointed by the right pointer and the right one pointed by the blue pointer. So if it's operated, it's definitely smaller than the highest one on the other side. So actually the height, the amount of water can be trapped on this position. It's only determined by the highest one on its left hand side if this element is pointed by the red pointer, or it's decided by the highest one on its right hand side if this element is pointed by the blue pointer. And we just continue doing so until the 2 pointers meet each other. And then just let's do the coding part. So here we need several. So the left pointer starts from 0, and the right pointer starts from the last one. Height or length minus 1, and left max equals to 0, and right max equals to 0, 2. And then while left is smaller than right, since we don't want the 2 pointers to meet each other, and then we first compare if height left is smaller than height right. If the left one is smaller, then we need to do the operations we described before, the conditional operations on the left hand side. So if height left is larger than left max, then we update the left max. And since this one is actually the highest one so far from the left hand side, there's nothing else left to help it trap the water. So clearly this position cannot hold water. Else we calculate the water, so we also need a variable to hold the result. So the result height left, so we need to subtract it from max, right? Okay, so here it is. And then after doing so, remember to increment the pointer. And the same thing also applies to the right hand side. So if right is larger than right dot max, right max, so we update the right max. Otherwise, we just calculate the unit of water trapped here. So we want to decrement the right pointer, and after all, we just return the results. All right, let's submit. Right, see, it's much faster. It's 0 millisecond. And let's analyze the complexity. The complexity for this algorithm is just there's only one loop, and this loop is n, so it's O(n). Why it's faster? Since previously it's actually 3n. Here it's only just 1n. So this is clearly gonna be faster. And talking about the space complexity, this is just O1 since there's fixed amounts of variables used. Additional variables used. So the space complexity of this algorithm is O1. And since we forgot to calculate the we need to also evaluate the space complexity of this element of this algorithm. So this algorithm here, there are like some O1 part, just some elements, some additional spaces used. However, the mainly used additional spaces is like these two additional arrays. So they are actually O(n) and O(n), and if we plus two O(n)s together, it's still O(n). So this one is actually worse than the second one. The first one is worse than the second one since the first one consumes O(n) space. Alright, and that's all. Thank you for watching. Bye.